In this lesson, we're going to go through a little bit of vocabulary to kind of get started on talking about polynomial functions. If you think about the word polynomial, that poly means many, and so we've talked a lot about monomials, binomials, and trinomials. So one-term, two-term, and three-term functions. If you think about a one-term function, that could be like something such as f of x equals 3. And so when we graph that, that'd be a horizontal line at y equals 3. Binomial is two terms, so those are our linear functions, where f of x equals 2x plus 7, let's say. That's a straight line when we graph it, but it's not horizontal, so it's going to be, different kinds of slope, positive or negative. Our trinomials are three terms. That's what we just got done studying in Chapter 6, and those are our parabolas. So that's when we have x squared plus 3x plus 7. So in this chapter, we're going to be studying all of those still, but we're going to add some polynomials that have four terms, or maybe have exponents that are different than what we're used to seeing. So first, to do the vocabulary, you'll see we have a polynomial in one variable. That's not going to come up a lot, but all that means is it contains only one variable. You're still going to have, if it's written as an equation, your function, you're going to have f of x still in there, but it's not going to have an x and a y. So if it says f of x equals 2x plus z, you know it's not a polynomial in one variable. This part of the equation, if they have this or they have this doesn't count as a different variable. They're saying after the equal sign, when I start writing something out, I can't have two different variables here. If they wrote something like 2x squared plus z, I now have two variables, so then it would no longer be a polynomial in one variable. The degree of the polynomial is your greatest exponent of the variable. So when you look, for example, this one I just wrote, my degree is my highest exponent. We're going to use that quite a bit because that's going to tell us how many answers we should have for our problem. So that becomes important when we use it for that. If I have an x cubed, an x to the fifth, whatever the highest exponent is, that's always the degree of my polynomial. And then the last one is the leading coefficient. That is the coefficient of the term with the highest degree. So, for example, if I have the following function, here's my function. My highest degree is my highest exponent, so that's this 4 right here. And I did write this problem in descending order. They maybe would sometimes not do that for you, though, so you have to kind of look at the equation. My highest degree is 4, so when I'm looking for the leading coefficient, remember coefficients are all the numbers in front of the variables. So my 3, 2, 9, and 7 is my coefficient. Sometimes when they're asked for leading coefficients, students will pick 9 because they think 9 is the biggest number, but we're actually looking at the number that is associated with the highest exponent. So the number with my x to the fourth, that coefficient is my leading coefficient, because when I write it in descending order, it should be the first one listed. So my leading coefficient for this problem would be 3. The other little piece is knowing the difference between the different types of equations. So we have a constant, linear, quadratic, and cubic. And we have studied constant, linear, and quadratic pretty in-depth. You should be mastering constant and linear. Quadratic we're getting really good at. We're almost at the point where we've mastered that. And cubic is kind of the new one we're going to add, and that's going to be something that we have not seen a lot of. We saw a few graphs of that in previous chapters, but that's one we haven't really worked with very much. So we'll talk a little bit more about that one today. An example of a constant equation would be something like y equals 6. So it equals a constant. There's no other variables in that problem, and if you think of the graph of that, it makes a horizontal line. A linear equation, hopefully you remember how to do that, but that's in the form of y equals mx plus b normally. And it wouldn't have to have the 6, so I don't want you to think it always has to be two terms, because this is also a linear function. So it wouldn't always have two terms, but it has to have x to the first. That's really what you're looking for, is that degree of 1 in this problem to make it linear. And the graph for that would be a straight line with either positive or negative slope. A quadratic function, an example of that would be y, not y squared, how about y equals x squared, and then you can add anything else you want. So I just put plus x minus 6. So there's a quadratic function, and the main thing that this one needs is it has to have an x to the second. That's an important piece here. If it doesn't have an x to the second, it's not quadratic. So my highest degree has to be a 2. And we've just got done studying those, so hopefully you realize those are parabolas that go up or down. If we're talking about functions, the sideways parabolas that we studied would not qualify for this because they are not functions. So these are not what we're talking about here, even though we've studied those. Those aren't functions. They could be equations if we're talking about equations, but they are not functions. So there could be they could distinguish between those for you. The one that I drew, hopefully you realize, goes up because a is positive 1. And then the new one is a cubic function. Our goal here is for our highest exponent to be cubed. So it could look something like this, and I'm just making one up. There's a cubic function. So what you're looking for to call it cubic is that its highest degree is a 3. Now what this means with these is each of these highest exponents tells you how many times this graph crosses the x-axis. So a linear function crosses the x-axis 1 time. A quadratic function crosses the x-axis 2 times. So a cubic function crosses the x-axis 3 times. And if you remember from when we've studied quadratics and we were looking for the zeros or the roots or the solutions, those were always our answers where the graph crossed the x-axis. If it didn't cross the x-axis, we knew that our solutions were imaginary. The same can be said for cubic. I need to have this graph cross the axis 3 times. What does that look like, you might wonder? Well, it looks like this. There's an example of a cubic function. You also, on the board in our room, you'll see one that goes like this. Obviously, this graph would only cross the x-axis once, which means that it happens to have 2 imaginary solutions also. You would find that you only have 3 or 1 time that it crosses the axis, because if it's imaginary, all the imaginary answers we've ever gotten are always plus or minus something like 2i, right? Imaginary solutions have to have a partner, so they always come in groups of 2. So there's no equation where the cubic function would cross the x-axis only twice. We could talk about double roots later, which is going to come into play, but for the most part that's a rule you can go with.